Welcome to the Foundry by Forge College. I am absolutely thrilled to have you here for this explainer. Think of today's session kind of like stepping into a high-performance mechanics workshop. So in our previous module, Robust Error Handling and Retry Strategies, we essentially built a tank. We created a deployment script that survives network failures beautifully using exponential-backoffs and idempotent operations. It's completely bulletproof. But well, there's one tiny problem. It drives exactly like a tank. Sure, it's safe, but man, it is slow. So today we're strapping a rocket engine to that tank. We're going to upgrade our robust deployment script to optimize it for speed and efficiency, and we're going to do it without losing a single ounce of that safety we worked so hard to build. Especially when you're deploying complex Solana programs or initializing dozens of accounts. We need this engine roaring. Okay, let's dive straight into our blueprint for today. First up, the need for speed. Second, parallelizing your deployment. Third, checkpoints and caching. Fourth, benchmarking the upgrades. And lastly, the final golden rules.
All right, Section 1, the need for speed.
Look, surviving a massive network failure, it feels fantastic. Honestly, when your script handles a dropped connection and doesn't crash, you feel like an absolute coding wizard. But now we gotta face the cold, hard reality of real-world constraints. When you're deploying complex Solana BPF programs or initializing just dozens and dozens of accounts, running everything sequentially, one by one, it just takes way too long. I mean, time is money, right? Waiting for a massive script to finish deploying synchronously is a massive drain on your resources. Imagine running a sequential script is literally like waiting in a massive line at a single grocery store register. You're stuck behind a guy paying entirely in loose change, using 20 different paper coupons. It's safe, and yeah, eventually everyone gets checked out, but it is excruciatingly slow. What we want to do instead is open up multiple registers. We want parallel execution. This allows independent tasks to check out simultaneously. It's fast, and if we do it right, it's every bit as safe.
But here's the million-dollar question, right? How do we go faster without completely breaking production? Because it is incredibly easy to make a script fast if you just rip out all the error handling. But we absolutely cannot do that. Our core challenge today is upgrading the engine for speed without removing the safety nets, like those idempotent operations and retry windows that we just painstakingly built. Basically, we need our script to be a high-speed bullet train, not a runaway freight train.
So Section 2, parallelizing your deployment. Let's open up the hood.
The very first step to parallelizing is opening up that hood and identifying which steps are actually independent. You obviously can't put the roof on a house before you pour the foundation, but you can upload different program artifacts at the exact same time. You can initialize completely unrelated accounts simultaneously. Finding these independent groups of tasks, that is your golden ticket. And to achieve that speed at a foundational level, we really need to embrace non-blocking I/O. If your script is just waiting for confirmations using blocking sleep loops, it's essentially frozen. By replacing synchronous file reads and sleep-based polling with asynchronous event-driven flows, you cut down orchestration latency dramatically. Your script is no longer sitting around twiddling its thumbs, it's firing off a request and immediately moving on to the next task while it waits for the answer.
Now hold on, we gotta be careful here. If you use unbounded parallelism, meaning if you just fire off every single task at the exact same millisecond, you are gonna hit Solana RPC rate limits instantly and basically DDoS your own connection. To prevent creating a massive traffic jam and saturating the endpoint, we use a semaphore. This acts as a concurrency limit, or a worker pool. I highly recommend using tools like Promise All Settled in Node.js or asynchronous.gather in Python combined with a semaphore. This ensures you only process, say, 8 concurrent requests at a time. It's controlled chaos, which, let's be real, is the absolute best kind of chaos.
Section 3, checkpoints and caching. Time to install the safety mechanisms that keep this new parallel highway from crashing.
We've talked about idempotency before, but in a parallel environment, the idempotent checkpoint becomes your absolute best friend. Think of these checkpoints as traffic lights for your worker threads. It's simply an atomic JSON record confirming a step's successful completion. So if a worker thread crashes mid-execution and we retry, this checkpoint ensures that concurrent retries just skip over any work that's already finished. It is the absolute foundation that prevents 2 concurrent attempts from producing an inconsistent, messy state on the blockchain.
Let's walk through this incredibly simple 3-step algorithm that every single parallel worker must follow. Step 1, check the checkpoint. Has this specific atomic step already been completed? If yes, skip it entirely. If no, move to step 2. Run the step, execute your expensive RPC calls, then immediately hit step 3, write the checkpoint.
Record that success atomically so absolutely no other worker ever tries to do it again. It is just a beautiful, self-regulating loop.
But hey, why stop at checkpoints? We can go even faster with caching and batching. Think of this as the carpooling lane of our deployment highway. If you find your script repeatedly looking up the exact same account state, cache those repeated RPC lookups in memory. Use a short time to live, or TTL, for values that change infrequently. And if you have multiple small fetches, batch them together using getMultipleAccounts RPC calls. Carpooling your requests like this drastically reduces round trips to the network, and that saves massive amounts of wall clock time.
Okay, moving on to Section 4, benchmarking the upgrades. Now, across all of our coding courses here at Forge College, we hold on to a core philosophy. You absolutely cannot improve what you do not measure, right? Guessing isn't engineering. So it is time to put our newly optimized script on the dyno tester. I want you to build a benchmark table exactly like the one outlined here in your own environment. Using high-resolution timers like process.hrtime in Node or time.perfcounter in Python, you need to actually capture these metrics. Run your baseline sequential script, record the total time, the RPC calls, the retries, then run your new parallelized cached script. Fill out the chart and mathematically prove to yourself that your median end-to-end time dropped significantly, all without increasing your error rate.
And once you've proven it's faster, well then I want you to break it. Seriously, I enthusiastically challenge you to induce a controlled failure, actively block an RPC call, or force a timeout right in the middle of a parallel stage. Why on earth would you do that? To validate that your retry windows trigger correctly, and most importantly, to prove that your checkpoints hold up. When the script recovers, the completed steps must stay completed, and only the failed task should rerun. Breaking your script on purpose is really the ultimate test of your safety nets.
We're in the home stretch now. Section 5, Final Golden Rules. Let's internalize the core philosophies of high-performance engineering.
First and foremost, and I really want to deliver this emphatically, separate correctness from speed. Actually, let me say that again. Separate correctness from speed. Do not even think about introducing parallel threads until your semantic safety nets are absolutely perfect. Your idempotency, your retries, your rollbacks, they must be bulletproof first. Without a rock-solid checkpointing layer, adding parallel execution is just begging for corrupted state and massive deployment nightmares. Correctness first, speed second.
All right, let's do a rapid-fire recap of our blueprint. Number 1, measure your baseline first, so you actually know what you're fixing. Number 2, optimize the critical path. Focus your parallelization on the independent steps that are actually taking up the most time. Number 3, favor controlled concurrency over unbounded chaos. Use those semaphores to protect your RPC endpoints. And number 4, maintain atomic checkpoints religiously. Remember, adding all this complexity, the extra threads, the synchronization logic, it is only worth it if it yields measurable time savings on that benchmark table.
So here is my final provocative thought for you to chew on. In a Web3 world where a single bug can literally cost millions of dollars, is your code fast because it's clever, or is it fast because it's truly safe? Really think about that balance. To explore a wealth of other Web3 topics and to continue mastering your Solana development journey, I highly encourage you to visit our website at forge.college. The learning never stops, guys. Thank you so much for joining me for this explainer, and I will see you in the next one.